Hi guys, this is the EdExcel A-Level Further Maths Paper 3 covering the Further Pure 1 FP1 module, and this is from the June 2019 series. Okay, so examiner's report wise for this paper, this paper offered plenty of opportunity for candidates of all ability levels to demonstrate what they learned. There were quite a couple of difficult questions in this paper. There's 2 points which the examiners mention. The first one is that when you are copying work from one line to the next, make sure that you're careful in that regard, because then if you're not, you could fall into some sort of errors. And the second thing is, if you draw a sketch where necessary, that will make your life a bit easier. Question number 1. We have to use the Simpson's rule with 4 intervals to estimate the integral of e to the power of x squared with respect to x in between the limits 0.4 and 2. And before we do that, we need to actually know what the Simpson's rule is. The Simpson's rule, that tells us that the integral of y with respect to x in between a and b is approximately h over 3 lots of the first y value plus 4 lots of the odd y values plus 2 lots of the even y values plus the last y value. Now we need to work out what h is. H, that's equal to the upper limit 2 minus the lower limit 0.4 over the number of intervals, which is 4. And working this out, we get a value of 0.4. Okay? Now we need to construct a table with x and y values. So let's quickly do that. We have our x values. We begin at this lower limit 0.4 and we go up in values of 0.4. So we have 0.4 to begin with, then 0.8, then 1.2, then 1.6, and then 2. Okay, we need to work out the corresponding y values. So when x is equal to 0.4, we have e to the power of 0.4 squared. Here we have e to the power of 0.8 squared. Here we have the value of e to the power of 1.2 squared. Here we have e to the power of 1.6 squared, and finally here we have e to the power of 2 squared. So these are our y values. And now we simply need to write down the odd and even values. So to do this, here the first value, that's y0, then we have y1, y2, y3, y4. Notice y0 is the first y value, y4 is the final y value, y1 and y3 are the odd y values, and y2 is the even y values. And then we substitute everything into the formula. So the integral from 0.4 to 2 of e to the power of x squared with respect to x, that's approximately equal to h over 3. So we have 0.4 over 3 lots of our first y value, e to the power of 0.4 squared, plus 4 lots of the odd y values. So we have 4 lots of e to the power of 0.8 squared plus e to the power of 1.6 squared plus y2, so that's e to the power of, plus 2 lots of e to the power of 1.2 squared plus y4, the last y value, so we have e to the power of 2 squared. And then we type all this into our calculator. So we have e to the power of 0.4 squared plus 4 lots of e to the power of 0.8 squared plus e to the power of 1.6 squared, and then we have 2 lots of e to the power of 1.2 squared, and then we have our final y value, that's e to the power of 2 squared, and then we multiply this by 0.4 over 3. We get a value of 16.47, etc., which to 3 significant figures we get 16.5. Okay, so this here is our final answer. Question 1 was regarding the Simpsons rule. This was a pretty decent question, quite straightforward. A lot of people made good attempts at this question. They scored the first 2 marks, but there were a couple of mistakes, which included the use of incorrect number of intervals and mislabeling of their ordinates so that their odds and evens were confused in the formula. So I think if you put it all into a table like this, it makes your life easy to substitute back over here. And there were some attempts of using the trapezium rule, which is incorrect. It said Simpsons rule. Question number 2. Given that k is a real non-zero constant and that y equals x cubed times by the sine of kx, we have to use Leibniz theorem to show that d5y over dx5 is equal to k squared x squared plus a lots of k cubed x cos kx plus b lots of k squared x squared plus c lots of k squared times by the sine of x, where a, b and c are integers to be determined. First of all, let's actually write down what this theorem is. So we have the theorem stated over here, dny over dxn, that's equal to the sum of n choose r of dru over dxr multiplied by dn minus rv over dx n minus r from r equals 0 to r equals n. And we've got y equals x cubed times by the sine of kx, and at this point it would be a good idea to label u, which is x cubed, and v, which is sine kx. We then need to work out the derivatives. We need to work out the first derivative to the 5th derivative, because here we need to show we have d5y over dx5 equaling something. So doing that, we begin with over here u equaling x cubed, okay, and we also have v, which is equal to the sine of kx. Working out the derivatives, du over dx, you'd find that to equal 3x squared. d squared u over dx squared, you'd find that to equal 6x. d cubed u over dx cubed, you'd find that to equal 6. Okay, let's move this up towards here a bit. the next derivative, d4u over dx4, you'd find that to equal 0. And finally, d5u over dx5, that's equal to 0. And then we do the same thing with v. dv over dx, you'd find that to equal k times by the cosine of kx. d squared v over dx squared, you'd find this to equal minus k squared times by the sine of kx. d cubed v over dx cubed, you'd find this to equal minus k cubed cosine of kx. d4v over dx4, you'd find this to equal k to the power of 4 times by the sine of kx. And finally, d5v over dx5, you'd find this to equal k to the power of 5 times by the cosine of kx. And having worked out the derivatives, we now need to substitute all these into this theorem over here. Okay, and doing that, we have d5y over dx5. This is equal to, well, if we use the formula starting off with r equaling 0, we have 5 choose 0 multiplied by u multiplied by d5v over dx5. The next term, we have 5 choose 1 du over dx multiplied by d4v over dx4. Okay, so let's just tidy that up. Next, we have 5 choose 2 d squared u over dx squared multiplied by d cubed v over dx cubed. Next, we have 5 choose 3 d cubed u over dx cubed multiplied by d squared v over dx squared. Next, we have 5 choose 4 lots of d4u over dx4 dv over dx5, sorry, just dv over dx, and then we have 5 choose 5 d5u over dx5 multiplied by v. Essentially, we've used the binomial expansion to arrive at this over here. And all we need to do now is simply substitute in everything. So substituting what we have, d5y over dx5, that's equal to, well here 5 choose 0, that's 1. And then we have u, which is x cubed. And then we have the fifth derivative of v, which is k to the 5 cos kx. And then we have 5 choose 1, which is 5. And then we have du over dx, which is 3x squared. And then we multiply this by the fourth derivative of v, that's k to the 4 sine kx. Next we have 5 choose 2, which is 10, multiplied by d squared u over dx squared, so we multiply by 6x, and then we multiply this by the third derivative of v, which is minus k cubed cos kx. Okay. Next we have, if I write this on a new line, we have 5 choose 3, which is 10. So we add on 10 times by the third derivative of u, which is 6, multiplied by the second derivative of v, which is minus k squared sine kx. Okay, let's just move this up a bit actually. And then finally, we have the remaining terms. 5 choose 4, that's 5. So we add on 5 times by the fourth derivative of u, which is 0, multiplied by the first derivative of v, that's k times by the cosine of kx, and then we have 5 choose 5, which is 1. We multiply this by the fifth derivative of u, which is 0, and then we multiply this by the function v, which is sine kx. Okay, and happily for us, you should recognize that this term and this term disappear, and if we tidy up the terms, d5y over dx to the 4, we have here x cubed k to the 5 cos kx, and then here we have 15 times by x squared times by k to the 4 sine kx, and then here we have minus 60 times by x times by k cubed cos kx, and then here we end up with minus 60 times by k squared times by the sine of kx. Okay, and if we now attempt to factorize, we see that d5y over dx5, well, if we look at the terms involving a cosine, you'd notice we have a k to the 5, well, in terms of what's common, a k cubed is common and the cosine kx is common, and what goes inside the bracket, we have k squared x squared minus 60, and then this is multiplied by k cubed x times by the cosine of kx. Okay, so that gives the term here and here, and then next you'll notice we have a 15 common to both. So we have 15, and then we have k squared x squared minus 4. And notice 15 times by minus 4 is minus 60. And then we have k squared sine kx. So that's the fifth derivative of y. And in conclusion, a is equal to minus 60, b that's equal to 15, and c that's equal to minus 4. Okay. Question 2 was concerning Leibniz theorem. A lot of candidates did well in this question. It was just finding derivatives. A lot of people did that well, which is good. There were a few candidates who were unable to make good progress in this question. Very few errors were seen in obtaining the derivatives that were required, and there were similarly few errors seen in the structure of the theorem. The most common error seen in this short question were errors when collecting terms to obtain a final answer. So I think that's on about over here somewhere, where you factorize out. And if it helps, if you want to multiply back in to make sure you get this, then you can do that. There's nothing wrong with that. Which other ones were there? There were also mistakes when copying from one line to the next. And then for those who are not familiar with this sort of problem, make sure that you are, for those who weren't familiar with this sort of problem, it was no binomial coefficients present. So I think if you know this formula and recognize that this bit is from the binomial coefficients, then you should be pretty decent on this question. Question number 3. We're given that dy over dx is equal to x minus y to the 5. This is our first equation. And we have to show that d5y over dx5, that's equal to ay times by d4y over dx4, plus b lots of dy over dx, lots of d cubed y over dx cubed, plus c lots of d squared y over dx squared squared. So this over here just requires us to work out the derivatives. So we begin with dy over dx equaling x minus y squared, and in this question we'd have to use implicit differentiation because we've got this y term over here which we need to differentiate with respect to x. So that's working out our our second derivative, d squared y over dx squared. Well, differentiating x we get 1, and differentiating minus y squared, that's minus 2y times by dy over dx. Okay. Next, our third derivative, d cubed y over dx cubed. Well, differentiating the 1 we get 0, and then we would have to now differentiate minus 2y times by dy over dx, and for this we'd have to use the product rule. So we have v times by u dash, so we have v, which is dy over dx, multiplied by u dash. Well, if I differentiate minus 2y, we get minus 2 lots of dy over dx. Okay, and then we add on u, so that's minus 2y lots of the derivative of dy over dx, which is d squared y over dx squared. So hopefully you can see we have minus 2y times by d squared y over dx to the dx squared, and then we subtract off 2 lots of dy over dx squared. Okay, so that's our third derivative done. With our fourth derivative, d4y over dx4, well, if we differentiate this minus 2y times by d squared y over dx squared, again we'd have to use the product rule. So we have v, which is d squared y over dx squared times by u dash, so we multiply this by minus 2 lots of dy over dx, okay, and then we have v times by u dash plus u, so we have minus 2y times by v dash, so we have d cubed y over dx cubed, okay. Now if we now take a look at this minus 2 times by the dy over dx all squared, over here we'd have to use the chain rule to differentiate this. So we have 2 times by the minus 2, which is minus 4, and then we multiply this by dy over dx, okay, and then we'd have to multiply by the differential of the bracket, which is d squared y over dx squared. So here we've used the chain rule or the bracket rule or whatever you call it. So if we tidy all this up, well, hopefully you can see that we have minus 6 lots of dy over dx, lots of d squared y over dx squared. So this is the minus 4 minus the 2, which gives a minus 6, and then we have the other terms. And then we subtract off 2y lots of d cubed y over dx cubed. Next, we have to work out the fifth derivative. So d5y over dx5. Well, if we differentiate this first term here, we'd have to use the product rule. So we have v, which is d squared y over dx squared, times by u dash, so we have minus 6 times by d squared y over dx squared. So we have v u dash plus u, which is minus 6 dy over dx, times by v dash. So differentiating this, we end up with d cubed v over dx cubed. Okay, and we've also got these other terms over here, which we need to differentiate again with the product rule. So we have v, which is d cubed y over dx4, times by u dash, so we have minus 2 dy over dx. So we have v u dash plus u, so plus u, times by v dash, so we have the differential of this, which is d4y over dx4. And if we tidy all this up, we have minus 2y d4y over dx4, and then we have minus this term, minus, so we have minus 6 lots of this, minus 2 lots of this, so we have minus 8 lots of dy over dx, lots of d cubed y over dx cubed, and then here we have minus 6 lots of d squared y over dx squared squared. And therefore, hopefully you can see the value of a is minus 2, the value of b, that's minus 8, the value of c, that's minus 6. Alright, so that was a bit of work, but hopefully you can see how we got there. We just used implicit differentiation quite a lot. Now for part B, we have to hence find a series solution in ascending powers of x as far as the term in x to the 5 of the differential equation over here, given that y equals 1 at x equals 0. So for part B, we'd have to look in the formula book, and because we're evaluating a series at the point x equals 0, we'd have to use our Maclaurin series over here. So let's just highlight what we need to use. We need to use this formula over here. So the first thing we need to do is work out all the derivatives at the point x equals 0. Well, to begin with, so this is part A. To begin with, when x is equal to 0, you'll see that y is equal to 1. We were told that in the question. And when x is equal to 0, dy over dx, we can work that out. So dy over dx, that's equal to 1 minus 2y times that's equal to x minus y squared. So we have x, which is 0, minus y squared. So we have 0 minus y squared, so y is equal to 1. It turns out we get minus 1. When x is equal to 0, d squared y over dx squared, that's equal to 1 minus 2y times dy over dx. So we have 1 minus 2y, so we have 1 minus 2 lots of 1 lots of dy over dx, that was equal to minus 1. Working this out, we get a value of 3. Next, when x is equal to 0, d cubed y over dx cubed, that's equal to minus 2y, so we have minus 2 lots of 1. Okay, lots of d squared y over dx squared, so that's 3. And then we have minus 2 lots of dy over dx squared. So we have minus 2 lots of dy over dx squared. So we have minus 2 lots of minus 1 squared. Working this out, we get minus 8. Next, when x is equal to 0, d4y over dx4, that's equal to, if you look over here, we have minus 6 lots of dy over dx. So we have minus 6 lots of minus 1. Okay, so we have minus 6 lots of minus 1. Lots of, if I go back, lots of d squared y over dx squared. So that was 3. And then we had minus 2y times by the third derivative. So we have minus 2 lots of y, lots of the third derivative, which was minus 8. Working this out, we get 34. Next, when x is equal to 0, the fifth derivative, that's equal to, if you look over here, that's equal to minus 2y times the fourth derivative. So we have minus 2 lots of 1 times the fourth derivative. And then we have minus 8 lots of y dash times by y triple dash. So we have minus 8 lots of minus 1 lots of minus 8. And then we have minus 6 lots of the second derivative squared. So we have minus 6 lots of 3 squared. It turns out we get minus 186. So what we've done over here is worked out all the derivatives at x equals 0. So that corresponds to f of 0, f dash of 0, f double dash of 0, etc. So now, if we put all this into our formula, y, that's equal to y of 0 plus x lots of y dash of 0 plus x squared over 2 factorial lots of y double dash of 0 plus x cubed over 3 factorial lots of y triple dash of 0 plus x to the 4 over 4 factorial lots of the fourth derivative at 0 plus x to the 5 over 5 factorial lots of the fifth derivative at 0, and then we have higher order terms. So substituting everything, we have y of 0, which we know to be 1, plus x lots of the first derivative at 0, that's minus 1, so we have minus x, and then we have x squared over 2 factorial, so that would be, well, and then we multiply that by the second derivative, so that's 3, so we add on x squared over 2 lots of 3, and then for the next term we have x cubed over 6 lots of the third derivative at 0, that's minus 8, so we times this by minus 8. Well, let's keep this consistent. Here we have x times by minus 1. Anyway, for the next one we have x to the 4 over 24, and then we multiply this by the fourth derivative at 0, which is 34, and then we have x to the 5 over 120 multiplied by the fifth derivative at 0, so that's minus 186. And then we have higher order terms. Don't forget to show those higher order terms. And therefore, in conclusion, y is equal to 1 minus 3x squared over 2. And then here we have minus 4x cubed over 3. And then here we have 17 x to the 4 over 12. And then here we have minus 31 x to the 5 over 20, and then we have higher order terms. Question 3, this was a pretty decent question. The first part was concerning finding the derivatives up to the fifth derivative, but the major errors were just were basically using the implicit differentiation sometimes, like over here, and collecting the terms together neatly, like so, and then over here using the chain rule as well. So those were the most common errors. And then for part B, that required us to use the Maclaurin series, because we're considering what happens when x equals 0. There were errors in calculations of the values of the derivatives seen, so that's this part over here. So there were errors over here, and that led to an incorrect answer. In terms of what else we can say is, when we talk about the final thing, over here people forgot to put the value of 1, which was a costly error as stated in the examiner's report. Question number 4. We have the parabola C, which has equation y squared equals 16x, and the distinct points P, which has coordinates p squared 4p, and Q, which has coordinates q squared 4q, lie on C, where p doesn't equal 0 and q doesn't equal 0. The tangent to C at P and the tangent to C at Q meet at the point R with coordinates minus 28, 6. We have to show that the area of the triangle PQR is 1331. So I think at this point it would be a good idea to sketch this problem. So what I've done over here is I've drawn out the problem. We've got our parabola C, y squared equals 16x, that's shown in red. And we've got the points P and Q, those are shown here. The tangent to C at P, that's shown in green over here. And the tangent to C at Q, that's shown in blue over here. Those two tangents meet at this point, minus 28, 6. And the reason the tangents are in these quadrants, I've just based it upon what R is. Okay, So that's the reason we have this shape. And it doesn't matter if P is over here or Q is over here. That doesn't make a difference. Okay? So we need to, first of all, before we find the area of PQR, we'd have to find the coordinates of P and Q. Now, let's do that by working out an equation for the tangent at P and Q. So, if we do that, if we consider this point P with coordinates P squared 4P, and the reason I haven't added these, the reason I've not written over here P squared 4P, I'm going to write the exact numerical values of those coordinates once I've worked out P and Q. So at this point P, we can first of all find out what dy over dx is. So before that, actually, what we need to do is work out what dy over dx is. We're given that y squared is equal to 16x. From here, it follows that dy over dx is equal to, well, if I differentiate the left hand side using implicit differentiation, we have 2y, lots of dy over dx, and on the right hand side, if I differentiate that, turns out we get 16. So therefore, hopefully you can, if I differentiate the left hand side we get this, and if I differentiate the right hand side we get this. Alright, so that was my slight mistake. From which we can see dy over dx, that's equal to 16 over 2y, so we have 8 over y as our derivative gradient function. Now, at the point P, with coordinates P squared 4P, we can now find out the value of the gradient at this point P. So this over here will equal, if we work this out, dy over dx, that's equal to 8 over y, so we have 8 over 4p, which is 2 over p. So the gradient of the tangent, that's equal to 2 over p. And with this we can find out the equation of the tangent. We have y minus y1 equals m lots of x minus x1. Okay, so in other words, if we substitute in our point for r, because we know r lies on the tangent at P, hopefully you can recognize that we have 6, which is the y coordinate of r, minus 4p equals 2 over p, lots of minus 28 minus p squared. Okay, so continuing to work this out, we have 6p minus 4p squared equals minus 56 lots of minus 2p squared. So in other words, we have 2p squared minus 6p minus 56 equals 0. So we can now solve for the value of p. If we solve this quadratic, we have 2p squared minus 6p minus 56. Solving this, we come out with 7 and minus 4. So p will obviously equal minus 4. The reason it equals minus 4, if you look at the coordinates over here, if I have p equaling minus 4, then we have 16 minus 16 as the coordinates of P. And that makes sense looking at where it is. Now the other value of 7, that corresponds to Q. And the reason it corresponds to Q is because to find out what Q is, we'd have to follow the exact same procedure as we did over here. So when we do that, instead of us having an equation in terms of P, we'd have an equation in terms of Q, and we'll end up with Q equaling 7. Okay, so I'll just write all that working down. So all I've just done over here is I've carried out the same procedure as before, and solving for Q this time we end up with 7. So hopefully it makes sense why P is minus 4 and Q is equal to 7. It's because of where I've based them, but you'd end up with the same sort of you would end up with the same quadratic, just with different variables, P and Q. So knowing that, what we can now do is state the coordinates of P. P when P is equal to 16 minus 16, and Q, that's equal to 49 and 28. Okay, so let's add those coordinates to the diagram. We have here 16 minus 16, and here we have 49 and 28. So we can now find out the coordinates of, knowing the coordinates of P, Q and R, we can now find out the area of the triangle PQR, and there's various different ways you can do this. One of the ways you can do this is to first of all work out the length of PQ, PR and RQ, then find out an angle between two of the sides, and then use the cosine rule to find out the you can use the cosine rule to find out one of the missing angles, and then use a half AB sine C to find out the missing area. Now that would take too long, but because we've got coordinates, we can actually use our vector knowledge to find out the area of PQR. I think at this point it would be a good idea to draw a quick sketch of the triangle we're concerned with. So if we draw out a quick sketch, we have something like this, okay? And if we add on the coordinates, we have P, 16 minus 16, Q with coordinates 49 and 28, and R with coordinates minus 28 and 6. So for us to find out the area of the triangle, we can find out the vectors RQ and also the vector RP, and then we can use the formula 1/2 times by the magnitude of RQ times RP. So if we do that, first of all, finding out what RQ is, RQ that's equal to OQ minus OR. So in column notation we have 49, 28 minus 28, 6. It turns out we get 77, 22. And PR, sorry, not PR, RP, that's equal to OP minus OR. So we have OP with coordinates 16 minus 16 minus 28 minus 28 6. It turns out we get 44 minus 22. Okay, so now multiplying these together, finding the magnitude and multiplying that by half, that will tell us that the area that's equal to 1/2 times by the magnitude of RQ times by the magnitude of RP. So we have 1/2 times by the magnitude of 7722 multiplied by 44 minus 22, and we can work this out using our calculator. So if we go to the vector menu, defining vector A with 2 dimensions, and you can even make it 3 dimensions with the k component equaling 0, it doesn't make a difference, but we have 7722, that's our first vector. Our next vector, that would be 44 minus 22, and multiplying those vectors together, it turns out we get 0, 0 minus 2662k. So we have minus 2662k. And of course this makes complete sense that we have 0, 0 for the I and j components and this value for the k component, because remember, multiplying 2 vectors together gives a normal to those vectors. Okay, and remember before the k components were 0, so therefore the normal vector to these vectors will be in the k direction. So working this out, finding out the magnitude of this, we get 1/2 times by 2662. So therefore the area of PQR, that's equal to 1331 units squared. Okay. Question 4, this was considering parabolas and then finding areas of triangles given coordinates. The most successful approach was to differentiate using the chain rule, so that's over here. I used implicit differentiation, and then substitute into the given general P or Q coordinates, so that's what we did over here, and you'd find that P and Q were exactly the same things except Q and P with the different variables used. And if you did that, you normally got the correct answer if you carried on working through that, well, up to here at least, finding the coordinates of P and Q. So what was said after this? This is quite interesting. The complexity of this algebra proved too much for some candidates. It was rare to see the resulting quadratic solved incorrectly, so that's on about this quadratic over here. But I think if you drew a diagram, then you can see what the coordinates of P and Q are, as I mentioned when I did the question. And then the second part, where we have to find the area of the triangle, this was quite difficult for a lot of people. A lot of candidates did not draw a sketch for this, which made it difficult for them, but those who did draw a sketch, that was done pretty well. Some people took a very long approach, and that was to use the cosine rule to find one of the angles, and then well, first of all, you have to find the length between each of the coordinates, and then use the cosine rule and find the area of a triangle by using a half AB sine C. But if you way that I did over here was, and that was just multiplying the vectors together and then taking the magnitude of that and multiplying, that'll give the correct answer, and this is the most efficient way that you can do it. We've got this integral 1 over 4 times by the cosine of x minus 3 times by the sine of x with respect to x. X is in between 0 and pi over 4. We have to use the substitution t equals tan of x upon 2 to show that the integral is equal to 1/5 times by the natural log of 2 plus tan of x upon 2 over 1 minus 2 times by tan of x upon 2 plus some arbitrary constant k. So it looks like a lot of work, this question, and it is. The first thing I would recommend that you do is write down the t formulae. Sin x, that's equal to 2t over 1 plus t squared. Okay. Cos x, that's equal to 1 minus t squared over 1 plus t squared. And then tan x, that's equal to 2t over 1 minus t squared. Okay, now the next thing we need to do is we need to put everything in terms of t. Hopefully that should be quite obvious from the question. But before we do that, we need to replace the dx into something involving t's. So let's do that in a different colour. So far we know that t is equal to tan of x upon 2, and if we differentiate t with respect to x, dt over dx, that's equal to 1/2 times by sec squared of x upon 2. Hopefully this is quite obvious, because we have to use, well, differentiating tan, we get sec squared, and then we multiply by the differential of the bracket, which is 1/2. Now, what this is the same as, sec, that's the same as 1 plus tan squared. So we have 1 plus tan squared of x upon 2, and using the fact that t is equal to tan of x upon 2, dt over dx, that's equal to 1/2 lots of 1 plus t squared, which is 1 plus t squared all upon 2. And therefore, knowing what dt over dx is, we want to find out what dx is. Hopefully here you can see that dx upon dt, that's equal to 2 over 1 plus t squared, and therefore dx, that's equal to 2 over 1 plus t squared dt. Now, I'd like to point out that this is a fairly standard result which you should know, and perhaps if I box this, I recommend that you just learn this over here, because whenever you've got integrals involving the t substitution, replacing dx with 2 upon 1 plus t squared dt is a fairly standard thing to do. So please do learn this result here. So what we can now do is replace everything as necessary. So the integral of the integral of 1 over 4 times by, what was the question? 4 times by the cosine of x minus 3 times by the sine of x with respect to x. If we replace as necessary, you'd find this to be equivalent to the following. We have, well, on the bottom we have 4 times by cos x. Cos x we just said was 1 minus t squared over 1 plus t squared. And then we have minus 3 sine x, so we have minus 3 lots of 2t over 1 plus t squared. And then On the top, obviously, we have 1. And we also have dx, which we just said is 2 over 1 plus t squared dt. And at this stage, I hope you can see that if you just consider these bottom, the denominator, hopefully you can see that the 1 plus t squareds cancel. So we're left with, on the bottom we have 4 lots of 1 minus t squared minus 3 lots of 2t. On the top we have 2. And then we have dt. Okay, and if we tidy all this up a bit more, this is the same as if I expand along the bottom, we have 4 minus 4t squared minus 6t. On the top we have 2. So dividing the top and bottom by 2, we have, well, if I divide by minus 2 on the top and bottom, we have 2t squared plus 3t minus 2 on the bottom. On the top we have minus 1, and then we have dt. And if we factorize this, on the bottom we have 2t minus 1 lots of t plus 2. Okay, so we wish to integrate this. Now, the reason I want to factorize this as this is, if I can somehow split this up into partial fractions, it makes the integration a tiny bit easier. So let's do that. Let's split this up into partial fractions. We'll do it in a different colour. We have minus 1 over 2t minus 1 lots of t plus 2. This is obviously the same as a over 2t minus 1 plus b over t plus 2. Okay, and multiplying through by 2t minus 1 lots of t plus 2, we have minus 1, which is equivalent to a lots of t plus 2 plus b lots of 2t minus 1. Okay, so with that we can now substitute in values to eliminate the brackets. So when t is equal to minus 2, for example, we have minus 1 on the left hand side, and on the right hand side the a bracket disappears. We're left with b lots of minus 4 minus 1, which is minus 5. So therefore b is equal to 1/5. And when t is equal to 1/2, on the left hand side we have the minus 1, on the right hand side the b bracket disappears, so we are left with 1/2 plus 2, which is 5/2. So we have a lots of 5/2, and solving for a is equal to 2/5. And knowing the values of a and b, well, hopefully you can see that we have the fifth as a common factor. Hopefully you can see that minus 1 over 2t minus 1 lots of t plus 2, this is equivalent to 1/5 lots of here we have minus 2/5. So here we have minus 2 over 2t minus 1 plus 1 over t plus 2. Okay. Now, you can look at the question and here we have 1 minus, well, if we use the fact that tan of x upon 2 is equal to t, on the top, hopefully you'll notice we have 2 plus t, and on the bottom we have 1 minus 2t. But over here, we've got a 2t minus 1. And if I bring this negative into the bottom, can you see that we have 1/5 lots of 2 over 1 minus 2t? Hopefully you'll recognize that this term and this term are exactly the same. And over here we have 1 over t plus 2. Hopefully that makes sense. And therefore, hopefully you can see that the integral then becomes, well, if you look at what we have over here, this bit we can replace with what we have over here. We have 1/5 lots of the integral of, well, I'll write this first. So we have, if I put this in brackets, we have 1 over t plus 2 plus 2 over 1 minus 2t. And we wish to integrate this with respect to t. So integrating, well, the 1/5 remains as a constant. So we have 1/5, and if we integrate 1 over t plus 2, we end up with the natural log of t plus 2. And if we integrate 2 over 1 minus 2t, we end up with minus the natural log of 1 minus 2t. And then we can combine these logs. So we have 1/5 times by the natural log of t plus 2 over 1 minus 2t. Okay? And don't forget we have a constant k. And therefore, what we can conclude is, knowing the fact that t is equal to x upon 2, we can conclude that this integral, if I just write it out, this integral over here is the same as 1/5 times by the natural log, just write this out neatly, times by the natural log of 2 plus tan of x upon 2 over 1 minus 2 times by tan of x upon 2 plus some constant k. And that's what we wanted to show. Okay? Question 5 was concerning the t formula, and we had to use that to solve some sort of an integral in terms of t. A lot of people managed to use the substitutions correctly here, but they forgot to replace the dx over here. And if you learn this result, it's a fairly standard result, and if you do that, it's just a fairly standard thing to do, to replace the dx with what we have over here. There were two routes you could do once you were at this stage. You can either split it up into partial fractions, which is what I did, or you can complete the square and then use the results from the formula book by making a substitution again. But with the partial fractions, this gave a couple of problems, particularly over here where we had the 2t, the minus 2 over 2t minus 1. If you bring the minus into the bottom, you end up with this over here, and I discussed that. Other candidates expressed their denominator in the form a squared minus x squared, or x squared minus a squared, and then this is a standard integral. Stage was the was simply this bit over here. And I always, when I did the question, I always looked back into what I wanted to show. and I think that would have helped. Question number 6, we have to, what does it say here? The concentration of a drug in the bloodstream of a patient T hours after the drug has been administered, where T is less than or equal to 6. This is modelled by the differential equation T squared lots of D squared C over dt squared minus 5T lots of dC over dt plus 8C equals T cubed. This is equation number 1, or I, and C is measured in micrograms per litre. And for part A, we have to show that the transformation T equals e to the power of x transforms this equation into this equation, d squared c over dx squared minus 6 lots of dc over dx plus 8c equals e to the 3x. So a lot of work for this question. For part A, we're gonna begin with our equation t squared lots of d squared c over dt squared minus 5t lots of dc over dt plus 8c equals t cubed. Okay, and we need to use the substitution t equals e to the power of x, and if I call this equation 1 and then this equation 2, we can differentiate this function over here, so dt over dx equals e to the power of x, and e to the power of x, that's equal to t, so dt over dx, that's equal to t. Now our goal is to replace all the t's with x's. Now if you look in the question, we have a dc over dx and a d squared c over dx squared, and we can find out what dc over dx is using the chain rule. dc over dx, that's equal to dc times by dt, sorry, dc over dt times by dt over dx. It's as though these dt's cancel out, and dt over dx, we've just found that to be t, so therefore dc over dx, that's equal to t lots of dc over dt. And do you notice, well, if I call this equation 3 first of all, hopefully you can notice we have over here a t lots of dc over dt, which eventually we can substitute back into this equation. We can now do a similar thing with d squared c over dx squared. This is where it gets a bit more complicated. First of all, d squared c over dx squared, that's the same as d over dx, so that's an instruction for us to differentiate dc over dx. Okay, and dc over dx, that's the same as t lots of dc over dt. So we wish to differentiate t lots of dc over dt, and here we'd have to use the chain rule because we have to differentiate this implicitly. Here inside the bracket, everything is in terms of t, and we wish to differentiate this with respect to x. And so for us to differentiate this thing with respect to x, we'd have to first of all differentiate with respect to t this thing, okay, dc over dt, and then we'd have to multiply by dx over dt, sorry, we'd have to multiply by dt over dx. It's as though these dt's cancel out, So all we've just done is applied the chain rule to expand this d over dx into an instruction of d over dt times by dt over dx. Okay, so we've expanded this out using the chain rule to give this over here. Now, t times by dc over dt, well, we can do this using the product rule. So we have v times by u dash, so we have dc over dt times by 1 plus t lots of the derivative of this other term d squared c over dt squared, and then obviously all of this is multiplied by dt over dx. And hopefully you can see, well, we have this dc over dt plus t lots of d squared c over dx lots of dt squared, dt over dx, that's simply t. And if we expand all this out, we have t lots of dc over dt plus t squared lots of d squared c over dt squared. And hopefully you can recognize that t lots of dc over dt is what we had over here. That's the same as dc over dx. So we have dc over dx plus t squared lots of d squared c over dt squared. This is the hard bit to get to. And just as we did before, if you look over here, we have t lots of dc over dt, and in the this bit is over here. So we need something for t squared d squared c over dt squared. And we can do that by rearranging this equation here to give t squared, sorry, to give it's a good way of putting it, yeah, to give t squared lots of d squared c over dt squared equals d squared c over dx squared minus dc over dt. And hopefully now this bit you can see, if I highlight it all, this bit over here is what we have over here. And therefore, if I call this equation number 4, we can now substitute in equation 2, which is this over here. So maybe if I actually highlight that, we can substitute in equation 2, equation 3 and equation 4 into equation 1. So we have this bit in yellow, which is d squared c over dx squared minus dc over dt, and then we have minus 5 lots of this equation here, so we have minus 5 lots of dc over dx, and then we have plus 8c, and this is equal to t cubed. Now equation 2, that's e to the power of x, so e to the power of x cubed this is the same as t cubed. And if we tidy all this up a bit, hopefully you can see d squared c over d squared c over dx squared minus 6 lots of dc over dx plus 8c. This is equal to e to the power of 3x. We'll call this equation 5. And that's what we wanted to show. Now for part B, hence find the general solution for the concentration C at time t hours. So for this, we would have to solve this second order differential equation, this non-homogeneous second order differential equation. First of all, our auxiliary equation, that would be m squared minus 6m plus 8 equals 0. Factorising, we have m minus 2 lots of m minus 4 equals 0, from which we see m is equal to 2, m is equal to 4. We have two distinct real roots, and therefore our homogeneous equation, that's equal to pe to the power of 2x plus qe to the power of 4x. Now, on the right hand side, we have a term involving e to the power of 3x, and therefore for the particular integral, we need to try something of the form c particular integral equals a times by e to the power of 3x. And if we differentiate this, dc over dx, this is equal to 3a e to the power of 3x, and d squared c over dx squared, that's equal to 9a e to the power of 3x. And we will substitute these back into our equation 5. So equation 5 then becomes, if we substitute in, we have 9a e to the power of 3x minus 6 lots of 3a e to the power of 3x plus 8 lots of a e to the power of 3x equals e to the power of 3x. And it should become obvious that the terms involving an e to the 3x cancel on all sides. So we are left with 9a minus 18a plus 8a equals 1. A, in conclusion, is equal to minus 1. And knowing that, we can therefore conclude that our particular integral is equal to minus e to the 3x. And therefore our general solution of C, that's equal to our homogeneous solution plus our particular integral. So we have pe to the 2x plus qe to the 4x minus e to the 3x. And we also know that t is equal to e to the power of x. And if we substitute back into this equation here, we can therefore see that our general solution is equal to qe to the qt to the 4 plus pt squared minus t cubed. Okay? So that's our general solution. And now for part C, given that when t equals 6, c equals 0, and dc over dt is equal to minus 36, we now have to find the maximum concentration of the drug in the bloodstream of the patient. So knowing that, what we can now do is, well, first of all, when t is equal to 6, c is equal to 0. So knowing that, we have q times by 6 to the 4, okay, plus p times by 6 squared minus 6 cubed equals 0. 6 to the 4, that's 1296. So we have 1296q plus 36p minus 216 equals 0. So let us say that this is equal to 216. Okay, so we'll call this equation number 6. And we were also told that when t equals 0, dc over dt is equal to minus 36. So if we take a look at this general solution, dc over dt, that's equal to, if we differentiate this, we have 4q t cubed plus 2p t minus 3t squared. Okay? And when t is equal to 6, dc over dt, that's equal to minus 36. So substituting in, we have 4q times by 6 cubed plus 2p times by 6 minus 3 times by 6 squared equals 36. So we have 4q times by 6 cubed, so that will be 864q, and then we have here 12p, and this is equal to minus 36. Let's do this on calculator. So we have minus 36 plus 108, which is 72. We'll call this equation number 7. And now we can solve equation 6 and equation 7 simultaneously. Okay. And if we do that, solving these equations simultaneously, we have, if we go to the simultaneous equation solver, we have 1296 plus 36 equals 216, and for the next one we have 864 plus 12 equals 72. Oh damn, meant to go to the simultaneous solver. So we've got 1296, 36, 216, and then here we've got 864, 12, 72. It turns out that P is equal to 0 and Q is equal to 6. Sorry, put these the wrong way around. Q is equal to 0, P is equal to 6. And knowing that, our particular solution of C is equal to 6t squared minus t cubed. Now, if you go back to the question, we want to find the maximum concentration, and the maximum concentration is when dc over dt is equal to 0. Okay, so dc particular solution over dt, so over dt, this is equal to 12t minus 3t squared. So we want dc over dt equaling 0. So we have 12t minus 3t squared equals 0. So we have 4t minus t squared equals 0. So let's just write this out neatly. And then we have t lots of 4 minus t equals 0, and therefore t is equal to 4. And knowing that t is equal to 4, we can now find out the max concentration. That's equal to 6 times by 4 squared minus 4 cubed, which is 32, and therefore C max, that's equal to 32 micrograms per litre. Okay. Question 6 was concerning differential equations, and we had to use a substitution to simplify the differential equation. Part A was actually quite hard in my opinion, and the main problem was finding the second derivative. But before that, let's see what was said. There were many incorrect attempts at applying both the product and the chain rule. It was also common to see candidates trying to fudge their answer to make it fit with the printed differential equation. The most successful approach seemed to be differentiating with respect to t, as we did over here, after obtaining dc over dt. Differentiating with respect to a different variable seemed to cause difficulties in O level, but the more prepared candidates, despite the fact that this is a very basic element at this A level, basically it was just this part over here. We had to just use the chain rule, and this was actually quite hard in my opinion to spot straight away. But we can expand the d over dt as we can expand this d over dx as d over dt lots of dt over dx. The reason being is because over here we have something involving t's, so we can't differentiate it with respect to x straight away. We'd have to differentiate it with respect to t first and then multiply by dt over dx. It's as though these cancel out. But if you could do that, then the rest of it just followed straight forward, and there's examples of this sort of question in the textbook, so please do practice that. The second part, solving this differential equation, that was quite straightforward for a lot of people. The only mistakes that were mentioned over here, some did not transform c into the function t. So if you look over here, once we obtained this over here, we had to use this substitution back to obtain something containing t's, and then part C we had to part C over here we just had to use our substitutions, and then once we found that, we had to find dc over dt to find the max, and then there were some who failed to give the correct units at the end, so do make sure that you do include that. Question number 7. With respect to a fixed origin O, the points A, B and C have coordinates 3, 4, 5, 10, minus 1, 5 and 4, 7, minus 9 respectively. The plane pi has equation 4x minus 8y plus z equals 2. The line segment AB meets the plane pi at the point P, and the line segment BC meets the plane pi at the point Q. For part A, we have to show that to 3 significant figures, the area of the quadrilateral APQC is 38.5. I think at this point it would be a good idea to sketch out the problem. So I've drawn out the problem. We've got L1, which corresponds to the line segment AB, and the line L2, that corresponds to the line segment BC. They both meet the plane pi at P and Q respectively. And the line segment AB, well, hopefully you can recognise that A will lie on this line. Let's just show that somewhere here. We have A lying somewhere on this line. And on this green line, the line BC, hopefully you can see C lies somewhere on this line. Okay, so we see that we have a quadrilateral APQC. So let's just sketch this quadrilateral out. Doesn't have to be accurate, but we have something looking like this. Okay, like I said, it doesn't have to be 100% accurate, but this over here is our quadrilateral. We have A, let's just show this here. We have A with coordinates 3, 4, 5. C over here with coordinates 10, minus 1, 5. 10, minus 1, 5. Here somewhere we have Q. We don't know the coordinates of Q. We'll fill those in later. And we've also got P over here somewhere. Alright, we don't know the coordinates of P just yet, but we can figure it out later. Okay, so hopefully you can see the problem we need to solve. We need to find the area of this shape over here. Now, before we do that, we need to find out the equation of L1 and the equation of L2. Alright, and once we've done that, we can substitute those back into this equation here to find out our parameters, and then from that we can find out the coordinates of P and Q. And with that, knowing the coordinates of P and Q, we can then find out the area of this shape. So first of all, we need to find out the what do we need to do? We need to find out AB first. AB, that's equal to OB minus OA. So we have 10 minus 1, 5, minus 3, 4, 5, and this is equal to 7 minus 5, 0. Alright, and then we've got BC. BC, that's equal to OC minus OB. So we have 4, 7 minus 9 minus 10 minus 1, 5. And if we work this out, we end up with minus 6, 8, minus 14. Okay, so we can now state the equation of line L1, which is AB. So the line L1, which is the line AB, that's equal to 3, 4, 5 plus lambda lots of 7 minus 5 and 0. Okay, and the line L2, that was shown in green here, the line L2, R is equal to 10 minus 1, 5 plus mu lots of minus 6, 8 and minus 14. Okay, now these lines over here intersect this plane pi. So if you want, you can therefore see over here that the general point over here R we can also rewrite as 3, 4, 5 plus 7 lambda minus 5 lambda plus 0 lambda. And this other one, we can rewrite this as 10 minus 1, 5, and here we have minus 6 mu plus 8 mu minus 14 mu. Okay. So having said all that, we can now substitute these back into our plain pi to find out the values of lambda and mu. And once we do that, we can find out the value of p and q. Of p and q. So if I call this, well, let's just do that. So doing that, we have 4 lots of this coordinate here of 3 plus 7 lambda, so that's the x coordinate, and then we have minus 8 lots of something, and then we have plus 5 lots of something equals 2. So we have here 4 minus 5 lambda, and here we have 5 plus 0. Sorry, here we just have 5 plus 0 lambda, and this is equal to 2. So with that, what we can hopefully see from here is we have 12 plus 28 lambda minus 32 plus 40 lambda plus 5 equals 2. 68 lambda minus 15 equals 2. So 68 lambda, that's equal to 17, and therefore lambda is equal to 1/4. That's quite straightforward. Okay, now for the next part, again same thing. So we have 4 lots of something minus 8 lots of something plus this last thing equals 2. And now if we substitute in this into this, we have 10 minus 6 mu minus 1 plus 8 mu and 5 minus 14 mu. And if we tidy all this up, we have 40 minus 24 mu plus 8 minus 64 mu plus 5 minus 14 mu equals 2. So we have minus 102 mu plus 53 equals 2. Minus 102 mu equals minus 51, and therefore mu is equal to 1/2. So knowing these values, we can now substitute back into here to state the values of p and q. So if we consider p we can find by, actually let's write it like this. We can find the coordinates of p. That will equal 3, 4, 5 plus 1/4 lots of 7 minus 5, 0. And working this out, we end up with 4.75, 2.75 and 5. Okay, and similarly RQ, that's equal to 10 minus 1, 5 plus 1/2 lots of minus 6 8 minus 14. So we have 7, 3 minus 2. Okay, so let's just add these into the diagram. We have 4.75, 2.75, and 5. And here we have 7, 3 minus 2. Okay, so stating the coordinates of P, we have 4.75, 2.75, and 5. And stating the coordinates of Q, we have 7, 3, minus 2. Now with that, what we can now do is split this triangle up. We can split it up into triangle APC and also triangle PQC. Okay, so let's just split this down the middle like so. And for us to figure out the area of this triangle and this triangle, we need the vectors here. We need the vectors AC and AP. And for the other one, we need the vectors QC and also QP. Alright, and once we've figured out those vectors, we can find out the area of this triangle and then this triangle, and then add up the areas together. So, we'll call this triangle 2, and this we'll call triangle 1. Okay, so we'll do this in orange. We can find out what AP is, first of all. We'll do it in orange. AP, that's equal to OP minus OA. So we have 4.75, 2.75, 5. And we subtract off 3, 4, 5. And doing this, we end up with 1.75 minus 1.25 and 0. Okay? And AC, that's equal to OC minus OA. So we have 4, 7, minus 9, minus 3, 4, 5. Working this out, we end up with 1, 3, minus 14. So the area of triangle APC, that's equal to 1/2 times the magnitude of AP times by AC. So working this out, we have 1/2 times by the magnitude of, well, if we multiply these vectors together, we need to multiply together 1.75 minus 1.25, 0, with 1, 3, minus 14. So working this out, we have 1/2 times by the magnitude of, and if we go to the vector section, define vector A, so we have 1.75 minus 1.25, 0. Define vector B. We need to define vector B. That's 1, 3, minus 14. So we have vector A times vector B So I've done something wrong here. So let's edit vector A. So we have 1.75 minus 1.25 and 0. Vector B, that's equal to 1. We need to edit that vector. So that was 1, 3, minus 14. And now multiplying them together, we end up with 17.5, 24.5, and 6.5. So we need to find the magnitude of this and then multiply it by half. So we have 1/2 times by 17.5 squared plus 24.5 squared plus 6.5 squared square rooted. So working this out, so we have the absolute value of this, and then if I times this by 1/2, we end up with 15.4008, etc. So let's store this into A. Okay, right, so that was that vector. So that's that area of the this triangle over here. So now we need to do the same thing for the other triangle. So next thing we need to do is find out what QC is. QC, that's equal to OC minus OQ. So we have 4, 7, minus 9, minus 7, 3, minus 2. We end up with minus 3, 4, minus 7. And OP, that's QP, that's equal to OP minus OQ. So we have 4.75, 2.75, 5, minus 7, 3, minus 2. And if we work this out, we end up with minus 2.25, minus 0.25, and 7. Okay, so similar thing to what we did over here. We now need to find out the area of PCQ, and that's equal to 1/2 times the magnitude of QC times by QP. Okay, so we have 1/2 times the magnitude of minus 3, 4, minus 7 multiplied by minus 2.25, minus 0.25, and 7. So finding out the magnitude of this, again go to our calculator, define vector C this time. So we have minus 3, 4, minus 7. Define the vector D, that would be minus 2.25, minus 0.25, 7. Just make sure I type that in right. So now multiplying those together, we end up with 26.25, 36.75, and 9.75. So we need to find the magnitude of this. So we have 1/2 times by 26.25 squared plus 36.75 squared plus 9.75 squared, and then square root. So working this out, we have the absolute value of this, and then we multiply this by a half, so we end up with a value of 23.1013, etc. Okay, so if I store this into B, we can therefore say that the area therefore is equal to the area of the triangle APC. Okay, so we have the area of the triangle APC and the area of the triangle PQC. So we have that area, which was 15.4008. So we have 15.4008, etc. And then we have this 23.1013, etc. We can therefore conclude that the area, if we add those together, so A plus B, that's equal to 38.502, etc. So we have 38.5 to 3 significant figures, and don't forget, state the units. Okay, so having done that, for part B, what do we have for part B? The point D has coordinates k for -1, where k is a constant, and given that the vectors AB, AC and AD form the edges of a parallelepiped of volume 226, we have to find the possible values of the constant D. Well, let's quickly sketch that out. Okay, so having drawn it, we've got A, B, C and D. We need to find the volume, and the volume is given by the magnitude of AD dot product with the product of AB times AC, and hopefully that makes sense from the diagram. So AB and AC, have we worked them out before? We should have somewhere. AB we've worked out, AC we should have also worked out. So let's write those down. AB, that's equal to, as we worked out before, 7 minus 5, 0, and AC, that's equal to 1, 3 minus 14. Okay, so now we need to work out what AD is. So AD, that's equal to OD minus OA. So we have K for -1 minus 3, 4, 5. So AD, that's K minus 3, 0, minus 6. Okay, so from here, what we can do is figure out the volume of AB times by AC. So we have 7 minus 5, 0, multiplied by 1, 3, minus 14. And the reason I want to do this is because the volume is equal to the magnitude of AD dot product with the product of AB times AC. Alright, so working this out, if we go to the menu, which we want to go to this menu, so let's define vector A, 7 minus 5, 0, and the other vector, let's define that to be 1, 3, minus 14. So we have this vector multiplied by this vector. It turns out we get 70 98 and 26. So we have 70, 98 and 26. Okay, so the volume therefore is equal to the magnitude of AD k minus 3, 0, minus 6 dot product with 70, 98 and 26. Okay, so working this out, the dot product, we have the magnitude of 7, let's get rid of this bracket. We have 70 lots of k minus 3 plus 0 lots of 98 plus 26 lots of minus 6. Okay, so tidying this up a bit, we end up with the magnitude of 70k minus 366. Okay, so we have this. So we have 70k minus 366 modded equals 226. The reason for that is, if you go back to the question, we were told somewhere the volume of this is 226. Okay, so this enables us to find the possible values of k. So if we go back down, solving this, well, we have plus minus 70k minus 366 equals 226. So dealing with the positive, we have 70k minus 366 equals 226. And if we deal with the negative one, we have 366 minus 70k equals 226. So here we have 70k equals 592, so therefore k is equal to 296 over 35, and for the other one we have 70k equals 140, k is equal to 2. So here we have our possible values of k. So therefore our answer, k is equal to 2 or 296 over 35. Okay. Question 7 was concerning finding the area of a quadrilateral. This seemed to give people a lot of problems, especially those who did not draw a diagram. A lot of people were happy with finding the intersection point between the lines and the plane to find the coordinates of P and Q, but the problem was basically over here. If you didn't draw a diagram, it was very difficult to see what's going on. There were a couple of attempts, there were a couple of errors stated over here. It was a very common error to see candidates attempt to evaluate the cross product, which would produce the area of a single triangle and then write down the given answer. There was another common problem which a diagram would have avoided, and that was overlapping triangles. For part B, that I thought was quite straightforward. We were to find the value of k given the volume of the parallelepiped. I think if you drew a diagram, that would have helped as well. Remember, we don't multiply by a sixth because it's not a tetrahedron. But overall, this question wasn't that well answered, which is quite surprising. It was long, yes, but it was quite straightforward. And there were also errors seen over here as well, right at the end when we take the magnitude. So please do be careful. This is nothing more difficult than what you see at your regular A-level maths, solving this equation here. Question number 8. The hyperbola h has equation x squared over 16 minus y squared over 9 equals 1. The line L1 is a tangent to h at the point P. P has coordinates 4 cos theta, 3 sine theta. The line L1 meets the x-axis at the point A. The line L2 is a tangent to H at the point 4, 0. The lines L1 and L2 meet at the point B, and the midpoint of AB is M. We have to show that as theta varies, a Cartesian equation for the locus of M is given by y squared equals 9 lots of 4 minus x over 4x, where x is in between P and Q. And P and Q are values to be determined. So at this point, I think it would be a good idea to show you an animation of what's going on. Okay, so let's have a look at this problem visually. We've got our hyperbola h that has equation x squared over 16 minus y squared over 9 equals 1. That's shown here. And let's show the asymptotes. We've got the asymptotes here. And we know that L1 is a tangent to H at the point P. P has coordinates 4 cos theta, 3 sin theta. So let's show the point P. P is over here somewhere. So P can be anywhere on the curve. Let's just put it over here, for example. And let's show a tangent to H at the point P. So we've got our tangent over here. Okay, and we've got this tangent L1 which meets the x-axis at the point A. That's shown here. And we've got the line L2 which is a tangent to H at the point 4, 0. So that tells us that L2 has equation x equals 4. That's shown here. And L1 and L2 meet at the point B. That's shown here. And the midpoint of AB is M. That's shown here. Now, when we talk about the locus of M as theta varies, what essentially we're saying is, as P moves, you can hopefully see M moves with it. So let's just slow this down a bit. Hopefully, you can see here that as P moves, M is also moving as well. So just pay attention to how M is moving over here. M is following some sort of an equation, and that equation it follows is y squared equals 9 lots of 4 minus x lots of 4 over x in between P and Q. So if we have this in orange, so M, hopefully you can see, follows that path shown in orange. Okay? So if we speed this up a bit, you can see M is following that path. Okay? So hopefully that demonstrates what we need to do in this question. Okay, so I've drawn out that diagram that I showed you in that quick animation. Let's just talk through everything once again, just to make sure that we can clarify everything. We've got our hyperbola h, that's shown in red. And we have this point P over here somewhere on the curve. And we've got the line L1, which is a tangent to H at the point P. We see that in grey over here. We see that L1 meets the x-axis at the point A. L2 is a tangent to H at the point 4, 0. So here is the point 4, 0. So let's just add this on. And here we also have minus 4, 0. We've got our asymptotes to the curve y equals minus 3/4 x and y equals 3/4 x over here. And the lines L1 and L2 meet at the point B over here. M is the midpoint of A and B, and as theta varies, M moves along this line over here. And this line is this equation here, y squared equals 9 lots of 4 minus x over 4x. And it actually becomes quite obvious that P and Q are 2 and 4 from here. Okay, so if we square root both sides, you can hopefully see that P is equal to 2 and Q is equal to 4. Okay, so having drawn that, let's just move all this a tiny bit up. So here we have the equation y equals 3/4 x. We begin, of course, with our equation x squared over 16 minus y squared over 9 equals 1. We'll call this equation 1. And because we're concerned with the tangent at P, let's differentiate this equation. So differentiating x squared over 16, we end up with x over 8. So we have x over 8, and then we have the differential of minus y squared over 9. Well, we have minus 2y over 9. And don't forget, we need to differentiate implicitly, so we multiply by dy over dx. And this is equal to the differential of 1, which is 0. So hopefully from here, if we do a slight bit of rearranging, you can hopefully see that dy over dx, if I multiply this by, that's a good way of doing this. Yeah, actually we'll write it out in full. We have 2y over 9 lots of dy over dx equals x over 8. So if we rearrange this equation for dy over dx, let's move this a bit here. So we have dy over dx, which is equal to x over 8 over 2y over 9, and therefore dy over dx. Hopefully you can see that is 9x over 16y. And at this point P, with coordinates 4 cos theta 3 sine theta, if we substitute this into dy over dx, hopefully you can see that dy over dx, that's equal to 9x. So we have 9 times by 4 cos theta over 16y. So we have 16 lots of 3 sine theta, which if we tidy this up, we end up with 3 cos theta over 4 sine theta. And we can now find out the equation of the tangent to h at P. We have y minus y1, so we have y minus 3 sine theta equals 3 cos theta over 4 sine theta lots of x minus 4 cos theta. Okay, so hopefully everything we've done so far isn't complicated. Now, if you go back to the question, we know that L1, so this over here, is the line L1. This meets the x-axis at the point A, and that obviously is when y is equal to 0. So when y is equal to 0, we have 0 minus 3 sine theta equals 3 cos theta over 4 sine theta lots of x minus 4 cos theta. And what we wish to do is find out the value of x, and from that we can state the coordinates of A. So multiplying through by this term over here, so multiplying through by 4 sine theta, on the left hand side we have minus 12 sine squared theta, and on the other side, if we expand out at the same time, we have 3 cos theta x minus 12 cos theta squared. And a bit more rearranging, we have 12 cos squared theta minus 12 sine theta. This is equal to 3 cos theta x, and we can factorize out a 12 here, so we have cos theta squared minus sine theta squared equals 3 cos theta x. And here this is the same as 1, so we have 12 times by 1, so 1 is the same as this over here. This is equal to 3 cos theta x, so therefore x is equal to 12 over 3 cos theta. So in conclusion, well, if we tidy this up here, x is equal to 4 over cos theta, and therefore the coordinates of A, that would be 4 over cos theta 0. So hopefully so far that makes sense what the coordinates of A is. So now we can find the coordinates of B. We know that B intersects L1 at the point x equals 4, because this equation over here is x equals 4. So let's just add this to the diagram. Here we have x equals 4. So with that, when x is equal to 4, what do we get? Well, we have y minus 3 sine theta equals 3 cos theta over 4 sine theta lots of x. Now we know x is equal to 4, so we have 4 minus 4 cos theta, and we wish to find out what y is, so we can find the coordinates of B. So if I multiply through by 4 sine theta, we end up with, on the left hand side, 4 sine theta y minus 12 sine theta squared, and this is equal to, well, if I multiply 3 times by 4 I get 12, so we end up with 12 cos theta, and then we have minus 12 cos squared theta. And a bit more rearranging, well, on the left hand side, if I take this term over to the left hand side, we have 4 sine theta y, plus 12 cos squared theta minus 12 sine theta squared. This is equal to 12 cos theta. And we can factorize out the 12 over here, so we have 12 lots of cos squared theta minus sine squared theta. Then we have this term still here, and this is equal to 12 cos theta. And again, we know that this over here is equal to the 1, as we said before. So we have 12 lots of 1. So we have 4 sine theta y plus 12 lots of 1 equals 12 cos theta. So we have 4 sine theta y equals 12 cos theta minus 12. So y, that's equal to 12 cos theta minus 12 over 4 sine theta, which if we divide the top and bottom by 4, we end up with 3 cos theta minus 3 over 4 sine theta. Okay, so knowing the value of y, we can state the coordinates of b. In conclusion, so this over here was the coordinates of a. The coordinates of b then would be 4, and the y coordinate of b would be 3 cos theta minus 3 over 4. Sorry, the 4 doesn't go here. Over sine theta. Okay. So knowing the values of the coordinates of a and b, we can state the coordinates of m. So m, that would have coordinates, if we work that out, we have 1/2 times by 4 plus 4 over cos theta. So that's the x coordinate of m, and the y coordinate would be 1/2 lots of this over here, 3 cos theta minus 3 over sine theta. Okay, so here we have the coordinates of m, and if we simplify this, m would have coordinates 2 plus 2 over cos theta in the x direction, and in the y direction we have 3 cos theta minus 3 over 2 sine theta. Okay, so now we know the coordinates of m, and we still need to arrive at this equation over here, shown in orange. And the way we can do that is, well, let's start labeling our equations before that. So here we have equation 1, here we have equation 2, here we have equation 3. What you can hopefully see from here is that the x coordinate of m, that's equal to 2 plus 2 over cos theta, and the y coordinate of m, that's equal to 3 cos theta minus 3 over 2 times by sine theta. Now, what we can now do is, first of all, we have to recognize that this over here, this y, tells us the path that m takes as theta varies. And as theta varies, obviously p will move, and as we showed in the animation, m goes along this orange path over here. So we now know the x and y coordinates of m in terms of theta, and obviously theta will vary. And we can combine these equations over here in parametric form, in some sense, if you want to think of it like that, into this Cartesian form over here. Hopefully that makes a bit of sense what I've said over there. So if I call this equation 4 and this equation 5, from equation 4, hopefully you can see that we have 2 over cos theta equals x minus 2, and therefore cos theta is equal to 2 over x minus 2. Okay, we'll call this equation 6. And if we take a look at equation 5, well, hopefully, if you go back to the question, you'll see that we have a y squared. So let's square that, what we have over here. If we square equation 5, we have y squared, so let's just quickly underline this. We have y squared equals 3 cos theta minus 3 over 2 sine theta squared. Okay, so what we can now do is tidy all this up a bit. So on the top we have 3 cos theta minus 3 all squared over 2 sine theta squared, and on the top we can factorize out a 3 squared, so we have 3 squared lots of cos theta minus 1 squared, and on the bottom we have over here 4 times by sine theta squared. Now, tidying this up even more, we have 9 times by cos theta squared minus 1 all squared over 4 sine theta squared. And if you look at what we have over in the question, that involved just x's. It's in Cartesian form. So what we can now do is we can use what we have over here in equation 6 and substitute in over here. But before we do that, you'll notice we have a sine squared, and we can rewrite that in terms of a cosine. So we have 9 times by cos squared theta minus 1 all squared on the top, and on the bottom we have 4 times by cos squared theta minus I've done something wrong here. Sorry, we don't have a squared here. That was my mistake, sorry. So on the bottom we have this. Okay. Yeah, that's correct. So all I've done over here is I've replaced this thing with this thing over here. They're exactly the same. We'll call this equation 7. Now if we substitute in equation 6 into 7, so now substitute in equation 6 into equation 7, doing that we have, just do this neatly, doing that we have y squared equals, well here we have 9 lots of cos theta, so we have 9 lots of 2 minus x minus 2 minus 1 all squared over 4 times by cos squared theta, so we have 2 over x minus 2 all squared minus 1. Okay, so hopefully that bit makes sense. And all we have to do is tidy all this up. So here we have 9 lots of, let's think of a good way to write this. We have 9 lots of 2 over x minus 2 minus 1 all squared, and on the bottom we have 4 lots of a difference of 2 squares. We've got 2 over x minus 2 all squared minus 1. Okay, hopefully that makes sense. So we have 2 over x minus 2 plus 1 lots of 2 over x minus 2 minus 1. Okay, and hopefully you can see that the terms cancel on the top and the bottom. So on the top we have 9 lots of 2 over x minus 2 minus 1, and on the bottom we have 4 lots of 2 over x minus 2 plus 1. And if we multiply through by x minus 2, we have 9 lots of 2 minus 1 lots of x minus 2. On the bottom we have 4 lots of 2 plus 1 lots of x minus 2. Continuing to tidy this up, we have 9 minus x plus 2, sorry, we have 9 lots of, start again, we have 9 lots of 2 minus x plus 2. On the bottom we have 4 lots of 2 plus x minus 2. So this simplifies to 9 lots of 4 minus x over 4x. Okay, so therefore y squared, that's equal to 9 lots of 4 minus x over 4x. Okay, and therefore, as we said before, if we square root both sides, well, let's just write this down. Y is equal to 9 lots of 4 minus x over 4x, and we have that on, we have the square root of that. So we have 3 lots of 4 minus x, well, I should write it out like this. We have 3 lots of 4 minus x square rooted over 2 lots of the square root of x. Okay, so therefore we can see that the value of p is equal to 2, the value of q is equal to 4. So let's just write this down. X is in between 2 and 4. Okay. Sorry, forgot part B. Let S be the focus of H that lies on the positive x-axis. We have to show that the distance from M to S is greater than 1. Okay, so first thing, if you go to your formula book for a hyperbola, let's just highlight this. For a hyperbola, that's got this equation over here. We've got the foci, which is plus minus AE0, okay? We're considering the positive one, so we have plus AE0. So let's just write this down. For part B, so all this actually was part A. And now for part B, the focus, we'll give the focus a coordinate of S that has a coordinate of AE0, okay? And show that the distance from M to S is greater than 1. So M to S must be greater than 1. So S could be here, for example. So what we can now do is, well, if we know the value of E, we can find out the what the focus is. We know A is equal to 4, and we can see A is equal to 4 from the form over here. So let's just write this down. A is equal to 4 and B is equal to 3. Hopefully that makes sense. So if we also go back over here for eccentricity, let's just write this down. We've also got B squared equals A squared lots of E squared minus 1. So using this information, we know what B and A are. So we have A squared, which is 9, equals B squared, which is equal to 9, and this is equal to A squared, 16, lots of E squared minus 1. So if we solve for E, we have 9 divided by 16 plus 1, square root this, we end up with 5 over 4. Okay? Remember, if you look from in the formula book, E is greater than 1, so we take the positive value. So we can therefore say that the focus is at x equals AE. So we have A, which is 4, times by E, which is 5 over 4, which is 5. And therefore S has coordinates 5, 0. Let's just add this to the diagram. So here we have 5, 0. And what did we have to show? We have to show that the distance from M to S is greater than 1. So the distance is equal to, well, when M is over here, when M lies on the positive x-axis, the distance is equal to 1. So when M moves across here, the distance is the difference. So we have over here, we can subtract 4 from the x coordinate of the focus. So what we can now do is say that D, this distance, is greater than 5 minus 4. So the distance is greater than 1. Okay? Question 8 was concerning a hyperbola. This was a pretty hard question in my opinion. Candidates appreciated the strategy to find the x-coordinate of the, basically the coordinate of A, but then the people made this quite hard by making unnecessary rearrangements over here first, before setting y equals 0. So if you set y equal to 0 first, it makes the life a bit more easier. What else could be said? There were also errors in finding the midpoint. The midpoint, people were subtracting rather than adding the coordinates, which is wrong. Establishing the form of the equation of the locus caused difficulty for many, and solutions were seen with much unhelpful algebraic manipulation. The strategy of finding cos theta in terms of x and then substituting into the expression for y squared from the midpoint was the most successful route, and it's the way I did. Working on both sides of the required expression to achieve a common expression was also used. Generally, neither was completed with a great deal of success, so it was a pretty bad question. Many getting bogged down on the algebra. I thought the algebra wasn't that hard. Even those who were successful in this manipulation, it was common to see no reference to the values of P and Q. So remember, the question did say, if you go back, P and Q are values to be determined. This was probably because there were many preoccupied with trying to obtain the equation of the locus of M, so probably just forgot. Of those who did attempt, Q equals 4 was seen, but P equals 0 was seen rather than P equals 2. Part B was quite difficult. A lot of people could not get beyond sort of this over here. I think if you drew a diagram, it would have made a bit more sense as to see what was required.